Hello, so this week's lecture we're going to do it remotely online, and I appreciate you bearing with me during this. We're going to talk about metamorphic rocks. All right, and I want to say, right before we get started, is I got a bunch of kids around here, and I might be interrupted one or two times, so please pardon the interruption. All right, so metamorphic rocks are pre-existing rocks are exposed to large amounts of heat and or pressure. And the parent rock, which is the parent material, it undergoes some sort of change, or what we call in geology a metamorphism. And so whenever a pre-existing rock undergoes some change or some metamorphism due to being exposed to large amounts of heat and or pressure, it forms what we call a metamorphic rock. So the metamorphism, the process in which a rock is changed by excuse me, results in either changes in the mineral content, the texture of the rock, and sometimes even the chemical composition of the pre-existing rock. And the degree to which a parent rock is changed during metamorphism is known as the metamorphic grade. And the metamorphic grade, it exists on a spectrum, and it can range anywhere from low grade, which occurs in the rock, when the parent rock is exposed to low temperatures and or pressures, and it can range up to high grade, where the parent rock has been significantly altered if exposed to high temperature and or pressures. So there is a range in temperature at which rocks undergo metamorphism. At low temperatures, those below 200 degrees centigrade, those are temperatures associated with surface conditions. And at those temperatures, we have the formation of sedimentary rock. And at temperatures above 700 degrees centigrade, we have rock melting, and so therefore we have the formation of igneous rock, and that molten rock solidifies. And so it's in between that range of about 200 to 700 degrees centigrade, that range in temperature in which metamorphism occurs, and pre-existing rock is altered into and changed, formed into a metamorphic rock. So what causes metamorphism? Well, a metamorphic agent is a process or phenomenon that alters a pre-existing rock and causes it to undergo a metamorphism. And metamorphic agents, they include heat, pressure, also known as stress, and chemically active fluids. So we will start with pressure. There's two types of pressure: confining pressure. So this is whenever the pressure is equal in all directions, acting inward on the rock. This causes the reduction in the pore space in between mineral grains and causes the rock to become more compact and increase in density. Then we have differential stress. Differential stress is when the pressure is larger in some directions than others. And this causes the rock to shorten in one direction, the direction in which the pressure or stress is the largest, and elongate in the directions perpendicular to that. So here in this image we have confining pressure, where if a rock is buried due to additional deposition of sediments, that increases the confining pressure, where the pressure is equal in all directions. Where, say, if the rock is caught up in a convergent plate boundary, it's going to have a significant amount of pressure in the direction of the convergence, and that pressure is going to be larger than the pressure vertically or along the convergence, and so it's going to be squeezed in what is called differential stress. And this causes the rock to shorten in the direction of the maximal stress and elongate in the directions perpendicular to that. Heat is another metamorphic agent. When rock is exposed to significant amounts of heat, the minerals that compose the rock recrystallize. And during this process of recrystallization, often happens is smaller, finer crystals will fuse together to form large, coarse, interlocking crystals. Heat can also increase the ease at which rocks are deformed when subjected to pressure. So sources of heat, well, they include if sedimentary rock is buried and pushed at deeper depths, it will be exposed to higher temperatures, because we know temperature increases with depth. Each one of these dashed red lines is called an isotherm, and along each of these lines you have a constant temperature. So this one is 300 degrees centigrade. Everywhere along this line, the temperature is 300 degrees centigrade, 600 and 900. So see if a rock is buried and pushed deeper, it will be exposed to higher temperatures. We could also have igneous activity, so the intrusion of molten rock into the crust. That molten rock will radiate heat into the surrounding country rock, and that rock will be exposed to that large amount of heat and be metamorphosed. And also subduction. Subduction, you have crustal rocks that are subducted down into the mantle, and as they're brought down, the temperature which those rocks are exposed to increases, and that exposes rock to higher temperatures as well. And finally, we have chemically active fluids. So when we have hot fluids, usually water, it's heated by thermal activity like igneous intrusion. That water can dissolve rock, and so the minerals, the atoms that are forming the minerals making up the rock, they dissolve into the water as ions, and then that water transfers the ions from one part of the crystalline structure to another within the same rock. Sometimes hot fluids contain dissolved ions from a different rock that has a different chemical composition, and if those foreign ions are precipitated out in a different rock, they'll actually change the chemical composition of that rock. And this process of chemically active fluids bringing dissolved minerals from other rocks and depositing them in new rocks, changing the chemical composition, is known as metasomatism. One example of where this happens is at divergent plate boundaries, where we have molten rock near the surface, and we have water seeping down through the oceanic crustal rock through cracks and fissures, and that water being heated by the heat being radiated off by the magma body. That very warm water dissolves minerals and transports them to other locations, metamorphosing rocks. So here you can see these black smokers. These are actually hydrothermal vents where heated water, subterranean water, is escaping into the ocean water, and it's called a black smoker because the water is so dark, it has so much ferromanganese, so many ferromagnesian silicates dissolved in it. So now we group metamorphic rocks into two different categories, foliated and non-foliated. Those are the two major groups of metamorphic rocks. Foliated metamorphic rocks have what is called foliation. And foliation is any planar arrangement of the mineral grains or structural features within a rock. Okay, so it's basically a non-random orientation of the mineral crystals inside of a rock. And this develops where the rock undergoes significant deformation. So how this foliation develops is that platy minerals inside the rock, they can rotate. Okay, that's one way. You can have minerals inside the rock recrystallize into new minerals that form parallel to one another. Or you can have spherically shaped grains that are flattened by the deformation. Those are three ways in which this foliation develops. Look at each one of these. So here we have these platy minerals that are randomly oriented. And then they're squeezed in one direction. You can see these large arrows indicating it's been squeezed in this direction. What happens is all these platy minerals, they rotate so that they are roughly parallel to each other, not completely parallel to each other, and roughly perpendicular to the direction they're being squeezed. In doing this, the rock takes up less space in the direction it's being squeezed and elongates in the direction perpendicular, which allows the rock to shorten in the direction it's being squeezed and lengthen in the other direction. So this is one way in which foliation develops, the rotation of platy minerals. Okay, then we can have recrystallization that produces new parallel minerals. So here we have shale. Shale is made up of sedimentary rock, clastic, and of these clay particles of clay. Now, clay are usually composed of flat minerals that they kind of align with one another because they settle on the sea floor, kind of flat. And so this shale you can see the bedding in it running up and down here. So the shale is on its side, and these clay minerals are running parallel to the bedding plane. But when this rock is squeezed, what happens to those clay minerals? They will recrystallize into new, more compact minerals that form extremely parallel to one another, like we see here. So whenever here we have these tightly packed chlorite and mica minerals. And so this develops a very strong foliation. And then we can have the flattening of spherically shaped grains. Okay, so if you have grains, say like in a sandstone, grains of sand, and if they're being squeezed, then these grains of sandstone can undergo what's called solid state creep, where they change shape while remaining solid. And this is by atomic bonds between atoms in the crystal lattice. They break and slip and reform with the next adjacent atom, and this occurs many times, allowing the crystal to change shape. And then you have the development of these flattened or elongated grains forming foliation. So there are different types of foliation. So we talked about different ways in which foliation can form, but there's different types of foliation depending on the grade of metamorphism. So the first, we're going to look at slaty cleavage, then we're going to look at schistosity, and finally gneissic texture. So slaty cleavage is a type of foliation that occurs during low-grade metamorphism. So what happens is little tiny clay minerals, they recrystallize into parallel and more compact chlorite and mica mineral crystals. And what happens is the rock can easily break or cleave along the planes parallel to the tiny little platy minerals, these chlorite and mica minerals. And so the rock can cleave into these flat slabs. And so slate does this very well. It has this cleavage where it breaks into these flat slabs. Now you can't see the foliation with the naked eye with slaty cleavage. You can only see the foliation in the fact that the rock breaks so cleanly along these flat parallel slabs. And so here we have some shale, some parent rock, it's shale, interbedded with some sandstone. If that rock is squeezed, what happens to these clay minerals that recrystallize into chlorite and mica minerals that are parallel to each other in perpendicular direction they're squeezed. So now the slaty cleavage will be along the plane perpendicular to the direction it's being squeezed. So these dashed lines mark the slaty cleavage. So these pieces of slate would cleave off this way. They cleave along these planes and cleave off this way. So I'm sure many of you have seen slate around. Slate, they used to make chalkboards out of slate, billiard or pool tables would be made out of slate. Slate's also used for roof tiles or pieces of sidewalk. And if you ever heard the statement, wipe the slate clean, that comes from the fact that they used to use slate for chalkboards. And then if you want to erase it, you wipe the slate clean to start over again. And so the reason why they've used slate for it is because it breaks into these nice flat slabs, and so it has these nice flat smooth surfaces. Next is schistosity. So any rock, any metamorphic rock that has this grade of foliation is known as a schist, and it occurs during medium grade metamorphism. What happens is those tiny chlorite and mica minerals that develop during low grade metamorphism to form slaty cleavage, they grow larger in size as the rock is squeezed even more. And so these chlorite minerals, they eventually break down and form nothing but the micas, biotite and muscovite. And these micas, they grow to large sizes to the point where you can visibly see them. And so in a schist, the muscovite and biotite minerals, they're arranged parallel to one another and perpendicular to the direction that the rock was squeezed. And so they are large enough to be seen. And you can see this layered texture where these these micas are layered on top of one another, and by looking at this image, we know that the rock was squeezed in this direction, right? Because you see the layering, you really see it here, is oriented like that. So they're parallel to each other and perpendicular to the direction it was squeezed. Finally, we have the foliated texture that develops under high-grade metamorphism, and this is what we call Gneissic texture. And what happens is the micas, they break down, they recrystallize into different minerals, and those minerals, they separate into bands, with ferromagnesian silicates separating, aggregating into bands, and non-ferromagnesian silicates aggregating into bands. So here, for example, we have quartz crystals, biotite, amphibole, and feldspar crystals. It's unmetamorphosed, and if it's squeezed in a significant amount, result in high-grade metamorphism. See that the ferromagnesian silicates, the amphibole, and the biotite, they accumulate into bands, and they separate from the quartz and the feldspar, which accumulate into bands. So the rock develops this banded texture, which is called a gneissic texture. So this is the highest grade metamorphism. You can see here in this rock, it was squeezed in this direction, perpendicular to the foliation. In this case, foliation is the banding of these silicate minerals. So here you could see the textures, different foliated textures. So here's the parent rock. This is shale, these little tiny clay minerals. So they were deposited on the sea, say a sea floor that was oriented like this. So they're roughly parallel to each other, and parallel to the surface they're deposited on. And this is magnified by 400 times. So these are really tiny crystals. So it's squeezed horizontally, and it develops a low-grade metamorphic texture, which is slaty cleavage. These clay minerals have recrystallized into chlorite and muscovite, tiny chlorite and muscovite mineral crystals that are parallel to each other, but perpendicular to the direction they're being squeezed. They're squeezed in this direction. You can see that these mineral crystals are about 10 times the size of the original clay minerals, because this is magnified 400 times and this is only magnified 40 times. And if this is squeezed even more, those micas, they grow in size, and see these large platy mineral crystals, these large micas and muscovite and biotite crystals. And you see there's no magnification here. You can see these mineral crystals with the naked eye. That is schist. It's a schistosity texture. And if it's squeezed even more, the highest grade metamorphism, the micas break down and into different silicate minerals, and the ferromagnesian silicates, they segregate into bands and they separate from the non-ferromagnesian silicates, which separate into bands. And this is the gneissic texture, which is forms from the highest grade of metamorphism. Right, that brings us to non-foliated metamorphic rocks. Okay. So non-foliated metamorphic rocks, they develop in environments where deformation is at a minimum. And because there's no significant deformation, the mineral grains, they do not acquire a arranged pattern or a non-random organization, and they remain randomly oriented. Okay, so non-foliated metamorphic rocks have randomly oriented mineral crystals. And the most common way to form non-foliated metamorphic rocks is whenever a rock is exposed to heat alone. So for example, this quartz sandstone, if you expose it to heat, what happens is these quartz grains, these grains of quartz sand, they will recrystallize and fuse together to form large interlocking crystals of quartz, forming the non-foliated metamorphic rock quartzite. Here, for example, here the original rock, the parent rock, or also known as a protolith, is sandstone. So you have grains of sand here, and the yellow is the cement. And it's exposed to heat, and the grains of sand, they fuse with one another and recrystallize into large interlocking mineral crystals forming a metamorphic rock, non-foliated metamorphic rock, quartzite. Same thing as limestone, you have the shelled fragments of organisms are made out of calcium carbonate. It's exposed to heat, the calcium carbonate, they kind of bleed together and recrystallize, forming large interlocking crystals of calcite, forming the non-foliated metamorphic rock, marble. So here you see an example of marble. Marble is just metamorphosed limestone. Limestone is subjected to heat. And quartzite, which is metamorphosed quartz sandstone. Sandstone is subjected to heat alone. So this is just a chart that has common metamorphic rocks, whether they're foliated or non-foliated, and their rock name, their grain size, some comments on them, and the original parent rock, which was metamorphosed to form them. Just for your reference. So now we have metamorphic environments, environments in which rocks are metamorphosed. These include contact, also known as thermal metamorphism, hydrothermal metamorphism, barrel metamorphism, subduction metamorphism, regional metamorphism, metamorphism along faults, and impact metamorphism. So contact or thermal metamorphism occurs whenever a rock is exposed to large amounts of heat being radiated off of intrusive igneous bodies. So for example, this magma body intruded into the crust here, heating this surrounding sedimentary rock. And that heat metamorphoses the surrounding rock, forming non-foliated metamorphic rocks. And the zone around the igneous intrusion, which is heated to the point of metamorphism, is called the metamorphic aureole, also known, sometimes commonly referred to as the baked zone. So, for example, if this was eroded, which this is what this would look like if it was eroded. We see this large igneous intrusion, so this igneous rock down here, granite, and above it we see this non-foliated metamorphic rock that was metamorphosed from whenever this was molten rock, radiating heat into this rock, causing it to metamorphose. So here we have these different layers or strata of sedimentary rock. This igneous intrusion intrudes in and radiates off heat, heating up the surrounding rock. And depending on the parent rock, we have different types of non-foliated metamorphic rocks formed. For example, a shell, once it's subjected to large amounts of heat, it forms a non-foliated metamorphic rock known as hornfels. When limestone is heated, it metamorphoses into marble, quartz sandstone into quartzite, and shale here into hornfels. Remember, this purple shaded region is known as the metamorphic aureole, also known as the baked zone. And the grade of metamorphism will be the highest right next to the igneous intrusion, and the grade of metamorphism will decrease with distance away from the igneous intrusion. So here we can see this was a lava flow, so this looks like some basalt that flowed over the surface and irradiated heat down into the shale that was below it, and it thermally or contact metamorphosed the shale, forming brick red shale, which is the form of hornfels. So you can see the color red, it changes with depth, where it becomes less and less and less red, and it kind of fades into the brown of the original host rock, which was the shale. So you can see how this has been metamorphosed to a higher grade, and the grade of metamorphism decreases with distance. Where here you have a sill, so this basalt intruded in between these two layers of dolostone. Dolostone is just, it's a darker limestone. Limestone has a lot of magnesium in it. But you can see where this heat radiated into the dolostone from the sill. That heat thermally metamorphosed the dolostone, forming marble. And so you can see the marble both above and below the sill, because both rock above and below was heated up. And so you can see marble formed in the metamorphic aureole, or the baked zone, on both sides of the sill. Now, hydrothermal metamorphism occurs whenever you have chemically active fluids. So this occurs at divergent plate boundaries, pretty much anytime you have molten rock near the surface. So it can occur along anywhere you have basically some volcanism. And so serpentine is a very common hydrothermally metamorphic rock. It's formed whenever ultramafic igneous rock, so peridotite, is infused with a bunch of water. And so this often forms at subduction zones, where water is subducted down into the mantle by the subducting oceanic lithosphere, and that water is released into the overriding mantle rock, hydrothermally metamorphosing. And that water is released, causing a hydrothermal metamorphism here by this subducting oceanic crust, subducting down, being exposed to these larger heats and pressure, and it itself metamorphosing. So whenever this oceanic crustal rock, which was formed at pressures and temperatures at the surface, when it's at these higher pressure and temperatures, it metamorphoses, which releases that water. So metamorphism in the subducting oceanic crustal rocks and metamorphism in the overriding mantle rock due to it being infused by water. And barometamorphism is also illustrated in this figure, where sediments from these mountains are transported and deposited in this basin. And as more and more sediments are deposited, the sedimentary rock is pushed down